Hello! In this video, we are going to prove the following theorem. Let A be a set. And suppose for all family of sets F, if the union of F is equal to A, then A is an element of F. Then A has exactly one element. Now, before we get into the proof, let's get a little bit of context. To start, if we recall, given any family of sets F, the union of F works in the following way. If X is any object, then X is an element of the union of F is equivalent to saying that there is some set A in F such that X is an element of A. Now, we have already shown that the union of the empty set is equal to the empty set. And finally, given any two sets A and B, the following is true. The union of A set minus B and B is equal to A if and only if B is a subset of A. Okay, so now let's get into proving the theorem. Now let's suppose that we've already declared our set A and we've already written down our hypothesis. So all we want to do now is show that A has exactly one element. Well, let's first show that A has at least one element. In other words, let's first show that A is non-empty. Well, assume for a contradiction that A is empty. Well then, if we take F to be the empty set, well then, the union of F is just the union of the empty set, which we know is equal to the empty set. And the empty set is equal to A. So, our choice of F satisfies the fact that the union of F is equal to A. Well, by our hypothesis, if this is true, then this is true. So we obtain that A is an element of F. And we know that F is equal to the empty set, so A is an element of the empty set. But this is a contradiction because the empty set has no elements. Our assumption that A is empty led us to a contradiction, so we must instead have that A is not empty. And since A is non-empty, this means that there is at least one element in A. I'll call it X. Now, we want to show that A has exactly one element. So we're going to show that X is the only element of A. In other words, we're going to show that A is equal to the singleton set of X. And to do so, let's consider the following family of sets. Let's consider the family of sets which contains A set minus the singleton set of X and the singleton set of X. Well, we're going to show that the union of G is equal to A. And if we can show that, we can apply our hypothesis to show that A is an element of G. Well, what is the union of G? The union of G is just the union of these two sets. What is this equal to? Well, by our third fact here, we know that the singleton set of X is a subset of A, so the union of this must be equal to A. So we see that the union of G is equal to A. So, by our hypothesis, A is an element of G. But remember, G only consists of two objects, this guy and this guy. So since A is an element of G, A must be equal to either this guy or this guy. Now we want to show that A is equal to the singleton set of X. Well, what happens if A is equal to this guy instead? Well, since X is an element of A, we have that X is an element of A set minus the singleton set of X. Which means X is not an element of the singleton set of X, but that's absurd. So our assumption that A is equal to A set minus the singleton set of X led us to a contradiction, so we must instead have that A is not equal to A set minus the singleton set of X. So putting this together, we have that either this is true or this is true. But we've eliminated the possibility that this is true, so we must instead have that this is true. So A is equal to the singleton set of X. This tells us that A has exactly one element, namely X. And that's exactly what we want to prove. So this completes the proof. And so yeah, that's pretty much it for this video.